Do I start? Yeah. Okay, so good afternoon, everybody. And many thanks to the organizers of this conference for having me here. It was a real pleasure. It is a real pleasure to be back here after quite a long time. And of course, it is a real pleasure to be here to celebrate the career of Massimo, who was my first mentor in astrophysics. So following the directions of the organizers, I will try to give you a brief review of progress in galaxy evolution, theoretical evolution, driven also by large surveys. So let me start with a few comments on the richness of data that has followed the explosion of digital surveys over the past decades or so. This is something that was touched before, just before lunch. I was looking for some quantitative data in the literature, and I found this paper in 2011. The data here was that about 1 petabyte of public data was electronically accessible in 2011, and that the data volume was growing at a rate of about 0.5 petabytes per year. Of course, the data volume increase will accelerate dramatically in the next few years because of new surveys and projects that are moving into operation, like LSST, Euclid, ALMA, SKA, etc. And the projection in 2011 was that by the end of this decade, the amount of data accessible to the public would be about 60 petabytes. Now, of course, this is an enormous amount of data, and the data storage is not, as I understand, is not the main and certainly not the most important issue. The main problem here is that you have to find new ways and develop more clever algorithms to search for this data and to analyze the data, of course. Now, what large samples have allowed us to appreciate that also that there is a multidimensionality in galaxy evolution. And this has showed, for example, that there are a number of the scaling relations that we have known for years are just projections of higher dimensionality distributions. And I'm sure Daniel will discuss this in more detail during his talk. So what is the influence of this data explosion in astronomy on theory? I think there are two most main effects that this has produced in the theoretical framework. First of all, there was a push, which is not just coming from surveys though, to work on larger and larger simulations. This is an example of a slide from the Millennium XXL simulation. This is a box of about 3 gigaparsec on one side. Also, there was the requirement from theoretical model to produce more and more sophisticated information and more observables to be compared with the observational data that are available. Also, in the theory, there has been the development of virtual observatories of the same kind that has been discussed just before lunch. And I think the experience that we had with these virtual observatories in theory has been very positive. It has shown that there is a lot of interest from the community, and that and the amount of papers that has been published using this way of publishing theoretical information has been quite large and is increasing. So let me now come to the main subject of this review, which is galaxy evolution. Galaxy evolution is a complicated subject, as you know, and the obvious and main reason for that is that it is not a single physical process, but it is the result of a network of complicated physical processes that act on vastly different scales and that are entangled in a complex network of actions, back reactions, and self-regulations. Nevertheless, in the past years, we have developed several techniques to study galaxy formation in a cosmological context. And one of these techniques is that goes under the name of semi-analytic models of galaxy formation. The choice of the name was not very lucky, I think, but what are semi-analytic models? Semi-analytic models are a tool to study galaxy formation. It's based on a simple yet theoretical and physically motivated prescriptions to model the evolution of the baryonic component. Modern semi-analytic models of galaxy formation are based on high-resolution n-body simulations that are used to that provide the location and evolution of dark matter substructures, dark matter halos, that are considered the birthplaces of luminous galaxies. Since pure n-body simulation is something that can be handled relatively easily, this method allows us to assess a very large dynamic range in mass and in spatial resolution, and also computational times are quite limited, which means that we can explore the parameter space in a reasonable amount of time. Of course, there is the disadvantage of using semi-analytic model is that galaxies are just arrays that carry a certain number of information, which is mass, metals, star formation rate, colors, etc. And they do not have spatial resolution, internal spatial resolution. And the hydrodynamics in this case is not treated explicitly. The advantage, which is instead the advantage of fully hydrodynamical simulations. As a tool to study galaxy formation, however, one should remember that hydrodynamical simulations are still computationally expensive, so that it is still relatively difficult to carry out high-resolution hydrodynamical simulations of cosmological volumes. And in addition, and most importantly, in my opinion, physical processes that drive galaxy formation and evolution still need to be included using what in the jargon is called subgrid physics. And also in this case, the name was not very good choice. I think it's quite misleading talking of subgrid physics, because it gives the impression that if you increase the resolution, you can overcome the problem, which is not quite true, because the problem is that we do not have a theory of star formation, for example. So we cannot model these physical processes ab initio. That's simply the situation, and I think this will be the situation for a large number of years still. So in the following, I will try to give you an overview of what is the status of theoretical modeling galaxy evolution, and for convenience, I will distinguish between central galaxies and satellite galaxies. This is a distinction that is obvious and also convenient from the theoretical point of view. It is not that obvious and not always easy from the observational point of view. Maybe it's somewhat easier for galaxy clusters, where you often, but not always, and this is an example, this is the center of the cluster with 2 BCG. In galaxy clusters, in many cases, you have one central dominant BCG, so it's easy to identify the central galaxy, and all the rest are satellite galaxies, but this in general is not easy. Though it is now routinely done in observational analysis with the aid of mock catalogs from galaxy formation models. So let's start with the central galaxies, and if we start with central galaxies, I have to start talking about the radio mode, the so-called radio mode feedback. Now, since the first X-ray maps of clusters became available, it was noted that the gas at the center of most galaxy clusters is apparently not cooling and forming stars, although the high X-ray emission would imply very short cooling times. This is known as the cooling flow problem, and there is large circumstantial evidence that AGN might play an important role in solving this conundrum. We see that circumstantial evidence ranges from the observation of cavities in the X-ray images of clusters. This is the Perseus cluster. To the demographics of radio loud galaxies, which are shown to be more abundant at the center of massive clusters. Radio mode feedback has become, over the past few years, a crucial ingredient in theoretical models of galaxy formation in order to avoid the excess of massive galaxies. And keep the stellar population of these massive galaxies old as it is observed. This is from a paper by Congresso and collaborators in 2006. This is the K-band mass function. This would be the prediction that you have if you do not suppress the condensation of gas at the center of massive clusters. This is what you get instead if you include a phenomenological model of AGN feedback. There are a number of different groups who are analyzing the effect of including AGN feedback in hydrodynamical simulations. There are different studies being carried out using different techniques of hydrodynamical simulation. This is from a paper, which is not the most recent one, but still is very I think demonstrated made clear some very important points. This is by Siachki and Springer in 2006. This is the X-ray map at the center. This is 400 kiloparsec. This is the central region of a massive cluster, about 10 to the 15 solar masses. And what they showed is that if you start injecting energy bubbles at the center of the cluster, you can indeed offset the cooling, but the efficiency of this offset depends crucially on a number of ingredients that are unknown, like gas viscosity, the geometry of the bubble injection, which is much more, the suppression of cooling flow is much more efficient if the injection of energy is constant along one direction, as it is in this plot, rather than random, as would be probably more naturally expected. One important thing to realize is that the inclusion of AGN feedback is important not only in the very central region of galaxy clusters, because it started being effective at higher redshift, and so was effective in removing the gas from the star-forming regions at higher redshift when the binding energy was lower, which means, for example, that we can influence significantly the metallicity profile in the in the intracluster medium, as it was shown, for example, in a recent paper by Laneges and collaborators. This is the observational data here, data points with error bars. Ignore all the lines but the green, which is a model that includes only feedback from supernova, and the red that includes also feedback from AGN. We see that it can influence the metallicity profile also on quite a large scales. Now, this AGN feedback, as I told you, is works very well in the way we implement it in galaxy formation models, in keeping the stellar population of the old galaxies relatively old. But it doesn't work. There is a problem with the stellar population of the most massive galaxies that might be related, at least to some degree, to the way we model the AGN feedback. And this is related to the metallicity of the brightest cluster galaxies. Here is a plot showing the metallicity mass relation for one particular model. This is true for all the models that you can find in the literature nowadays. This is the purple line here are observational data from the SDSS. The red line here is the prediction from the models. You see that yes, there is a mass metallicity relation, but there is a problem with the normalization, which might be related to the yield. But most importantly, there is a bending here at the most massive end. that brings the model results away from the observational data. So the stellar population of these massive galaxies is metal poor, which is not what we observe. These are the points here are central galaxies of big halos, of 10 to the 15 solar mass halos. While observations suggest that brightest classic galaxies are as metal-rich as the most massive ellipticals. The problem in the models is that these galaxies have formed their stars, and this is something that Mike was saying earlier this morning, have formed their stars early in different progenitors on short time scales. These progenitors were assembled later on, but the time scale over which star formation occurred is very short. It's so short that it's not enough to bring the metal content of these galaxies to the level that is observed. And this is something that is not clear we can solve with playing around with the AGN feedback. You can see that from this plot here. This is the distribution. If you look at the black histogram, this is the distribution of ages and metallicities of these brightest cluster galaxies in this particular model. The red line is what you get if you switch off completely the AGN feedback. You see that you get a much younger stellar population because there is gas that is cooling and forming stars late. This star formation is not enough to increase significantly the metallicity of these galaxies. The purple histogram is what you get if you instead modify the feedback from supernovae. In this case, you see that you have a more modest decrease in stellar age, a much more significant increase in stellar metallicity. Unfortunately, this model doesn't match the observed galaxy mass function at redshift 0 though. So my personal opinion is that this is much more a problem that is related to the way we model the self-regulation between a star formation and feedback rather than the AGN feedback itself. The formation of the brightest cluster galaxies is something that is related also to the formation of another baryonic component, that is the diffuse stellar component. The formation of this component has been studied in detail using numerical simulation. This is from a paper by Morante and collaborators back in 2006, who claimed that most of the intercluster stars is coming from unbinding of stars that are associated with mergers leading to the formation of the brightest cluster galaxies. This is the fraction of diffuse stellar component that is coming from this physical process, unbinding of stars during mergers, and this is the fraction that is coming from stripping as a function of galaxy mass. So you see that the low mass galaxies are mostly contributing to the diffuse light through stripping, while for the most massive galaxies, this is mainly coming through mergers. Unfortunately, the problem with the intercluster light component, the diffuse light component in the simulation, is that the results from simulations do not converge. If you increase the resolution, you increase the amount of diffuse light that is detected, which is clearly a sign that there is some numerical effect that is there and that we do not have under control. And I think one clear demonstration that there is also that there are many problems came from a paper by Hoekman and collaborators a few years back. This is the fraction of stars that are formed as a function of the distance from the halo center. The red line here for satellite galaxies, the green histogram is for the BCG, and the blue histogram is for the ICL. So you see that while the satellite and the BCG are forming inside the halos, a significant fraction of the ICL is forming outside the halos. These stars are forming from gas that is stripped from infalling structure and is being compressed. And this is something that might not happen if instead of using SPH, you would use a different scheme for solving the hydrodynamics. It is, for example, Eulerian codes. And this is something that different groups are now studying. Nothing came out yet, but it's certainly something to keep in mind. So let's move now to the satellite galaxies, and let me start from the basic observation for the satellite population, for the galaxy population in general. That is the galaxy mass function or luminosity function. The problem will be similar in that case. This is from a recent paper by Benedetta Vulcani, who compared the mass function measured from two different surveys of galaxy clusters, WINGS, and Bianca will discuss more about WINGS later during the week, and EDISC's target redshift. The observations here are in blue, while predictions from the models are in red. You can see that there are two different problems here. One is at the massive end, which is maybe not that serious because the statistics here is low and you see that the error bars are much larger. But there is a much more serious problem that is at the low to intermediate mass scale. That is that the model tends to overpredict significantly the number densities of these galaxies over this mass scale. This is something that is true for the general field, as was pointed out in some earlier work by Fabio Fontanot back in 2009, is more dramatic in galaxy clusters. And this is a problem that has not found a solution yet, at least to my opinion, and discussing this a little bit more, is a difficult solution to find because as we demonstrated, the problem originates from an excess of central galaxies in halos with the velocities, the circular velocities of the order of 100 to 200 kilometers per second. These are galaxies that you cannot easily destroy by increasing the supernova feedback, because if you do that, then you would deplete the amount of galaxies on a range that is very well populated at lower redshift. This is from a very recent paper that has been published by Enriquez and collaborators in 2013. This is in this paper, what they have done is to use a semi-analytic model of galaxy formation coupled to a Monte Carlo Markov chain to identify the combination of parameters that would best fit the galaxy mass function at redshift 0 and all these previous redshifts you see. So this is not a prediction. This is a consistency check, right? Because this is this was the requirement of the Monte Carlo Markov chain, that it would the model would fit all these mass functions, and it does. You should look at the solid line. You see that it fits very well the galaxy stellar mass function at redshift 0 back to redshift 3 or so. And the way they managed to do this is to modify the reincorporation timescale of gas that has been previously ejected by supernova explosions. So by modifying the feedback scheme, the supernova feedback scheme that is used in the model. This model is not, still has other problems with satellite galaxies. I will discuss the other problem in a minute. The other problem is that the Monte Carlo Markov chain forces them to assume some extreme values for some of the parameters that are used. For example, the yield in this model is about 0.05, that is much larger than what is observed. So it's not clear to me, I'm not yet convinced that this is a plausible solution to the problem I just discussed. Another problem, another long-standing problem with satellite galaxies is their color, their stellar population. What has been known since 2006, this is from a paper by Simone Weinman, is that models tend to predict the satellite population coming from model is too old with respect to what is observed. Most of the satellite galaxies in our models are red and passive. While in the observational data, and this is came from SDSS, you will see that the fraction of blue galaxies is relatively high and is increasing with increasing luminosity, decreasing luminosity. For some time, it was thought that at least people working on these models, we thought at the beginning that the problem would be the fact that we are the way we model satellite galaxies is that we assume they have a reservoir of hot material that can cool and form stars. And then when these galaxies become satellites, we assume that this reservoir is instantaneously stripped. And we thought maybe we shouldn't do this instantaneously. And indeed, there were a number of simulations going and studying this problem immediately, and they found that yes, the hot halo should survive there for some time. It is, though, dramatically reduced after the first pericentric passage, and it seems to be there for some time, only for the most massive satellites. So now, the consequence is that most of the models you can find in the literature, virtually all of them, include non-instantaneous stripping, but still they tend to under-predict the fraction of active satellites. So still, this was not enough to bring our satellite population to the active level that is observed. And this is actually quite a tough problem in my opinion, is one of the most difficult problems to solve nowadays, because observations, this is from a paper by Penn and collaborators, but it's not the only one who has found this. This is the relation between the star formation rate and the stellar mass for galaxies in two different environments. This is an overdense environment. Sorry, I think it's the other way around. This is but they are the same anyway. So one is underdense and one is overdense. Now, if the overdense environment is dominated by satellite galaxies, and it should be, though there are many caveats, I will measure the environment, etc. The implication on this plot is that satellite galaxies are forming stars at the same level than central galaxies of the same stellar mass. And they seem to be doing so for a relatively long time. And this is a very tough constraint for galaxy formation model, where by construction, satellite galaxies and central galaxies are different, are treated different. So, and I think I have done. I want to leave you with a few take-home messages. There are a few problems that are common to all galaxy formation models. And when I say galaxy formation models, I mean both semi-analytic models and hydrodynamical simulations. These problems are common to all these models that have been published in recent years. In particular, there is an over-prediction of galaxies of low to intermediate mass. The stellar population of these galaxies are wrong, both for low mass galaxies and for the highest mass galaxies in terms of metallicity, at least. And the consensus, I think, is that the problem is in the way we model the self-regulation between the star formation and so people in the community are now working in particular on these two physical processes to improve our understanding of the evolution of galaxies. I was started my review commenting on the data tsunami that has just started. This will become more dramatic in the next decades or so, and as more and more data are coming, of course, this means that more and more information are required from theoretical models that should also be modified to include other observables. For example, modeling the transition between the atomic and molecular component will be crucial for having detailed predictions for SKA, etc. And also, it's important to have a detailed modeling of the different chemical elements. Finally, I'd like to comment on the fact that, at least my personal experience with the database, virtual data observatory, and I had direct experience with the German virtual observatory, was very positive. At the beginning, I have to admit that as a theorist, I was very skeptical. And I think it was very positive experience, but from for the feedback we had from the community, it clearly demonstrated that people are interested in having and using this data, and this in turn can lead to a more rapid refinement and verification of our theoretical modeling. And I will stop here. Thank you.
Question. Michael? Oh.
Gabriella, thank you for this inspiring talk. My question is biased towards the brightest cluster galaxy, as you imagine. And I was thinking, when you show the plot of the metallicity versus total mass, how do you determine this metallicity? It's luminosity weighted. Is the metallicity only in the center part? And how do you associate a metallicity value to galaxies that can be as large as 100 kiloparsec? That is one question. And the second question is, what can you say of the metallicity gradient as function of radius?
That's a very good point. So, because as I said, at some point in semi-analytic models, of course, you don't have the internal spatial resolution of the galaxies. So what I call metallicity here is a total metallicity. Total in terms of abundances and total in terms of what is my BCG. So in terms of gradients, I cannot do much with semi-analytics. But what I have tested is that if I exclude all the stars that were accreted below redshift 1 or so, which presumably are going to the outskirts, this is not changed significantly. The other thing is that I have now a model that includes a sophisticated chemical enrichment model, so I am able to trace different elements, and also I account for the delay in chemical enrichment, which was not included in this model, and the problem is still there. The problem is there also if you use hydrodynamical simulations, where you can do more sophisticated radial gradient arguments. So I think it's quite robust in terms of, at least it is something that is found, that I see is common to all models that have been published in the last years.
Thank you. There's another question over, yeah.
Gabriele, I'm sorry if I repeat a question that I made in another situation, but I was wondering, in Trieste, Parisi Sucaciotti presented some models in which he was saying that maybe you don't always need AGN feedback to explain the properties of the ETGs, and you don't need AGN feedback. And I keep asking myself if all the community that's doing simulation agreed that without AGN feedback you cannot represent anything, or there are other explanations possible?
I think there was a wave of AGN feedback funds around 2006. People were all saying, oh, AGN feedback does everything. And I think now, finally, the community agrees that AGN feedback does something, but not everything. And certainly it's not important to explain the properties of, all the properties of most massive galaxies or elliptical galaxies in general. I think it is certainly needed, at least the radio mode feedback I'm talking now, at the very center of the most massive clusters, where you see observationally that there is a problem. Now, we think that AGN feedback plays a role in that, and we infer this from the observations. This doesn't mean that the way we model it is right. Actually, I think there are many indications that we don't do this properly yet.
Time for one very quick question, or quick question and quick answer. And here? You're right. There.
Gabriele, I agree. This problem is common and it's quite hard, and it also affects massive galaxies independently of whether they are brightest cluster galaxies. Yeah. You have to assume an AMF in this simulation, and the AMF is also playing a crucial role in metallicity. And if we buy the theory that the most massive galaxy will have a bottom heavy AMF or a top light, this problem is going to become even more severe because you lack the injection of oxygen when this supernova type 2.
Yeah,
We tried to simulate
we are working on that with Fabio because I mean, if of course you can vary the initial mass function in these models, but then you also want to self-consistently model the evolution and renormalize the model and do everything in a self-consistent way. So this is something that we are working on now.
Okay, thank you. So the next speaker is Daniel Thomas from Portsmouth.
Okay. First of all, thank you very much to the organizers to inviting me here. It's a great pleasure and an honor to take part in this wonderful conference in honor of Massimo Capaccioli. I will be talking about what we've learned from the Sloan Digital Sky Survey and also what we're going to learn from it, because I will take you, well, skipping over Sloan 3 basically, but starting from the first years of Sloan all the way to what we are currently doing in Sloan 4. Just a very quick summary. I think we all know what Sloan is, but just to get this back into our minds. Let me just make sure. Okay. I think one of the reasons why Sloan was so successful was that it was a combination of imaging and spectroscopic survey, covering for the first time very large areas on the sky. So imaged, now it is 10,000 square degrees in a number of bands, all the optical bands, and of course then providing spectra of a large fraction of those galaxies, so that redshift and many other galaxy properties could be determined at a very good spectral resolution and a phenomenal wavelength coverage, of course. And in this way, while originally, actually, I think historically it's quite interesting, the idea of Sloan was to cover large-scale structure in the universe, which of course it did, and did contribute important things too, but we learned far more than was anticipated and expected from analyzing the galaxy populations. And that's what I want to briefly summarize in a few slides, just a few highlights that from my personal view, of course, by no means comprehensive. One of the things, of course, once you cover a full galaxy population, what can you do? A game that now is routine, but I think Sloan has really revolutionized the field, is something like a mass or luminosity function of galaxies. This is the kind of plot we know from the early work from Paul Schechter, and then Bruno Bingali and collaborators, they like to slice these things up. Now you don't really see data here, these are the fits, but I think if you looked at the data, you knew that these are very handful galaxies. This sort of work is being done. If you look at the environment, you look at Coma and Virgo as clusters, just those two basically, and some other groups, and what is called field, and the handful of galaxies that remained. And then Bruno Bingali, I think, was always complaining about the simple Schechter function being too simple here. And certainly Sloan helped us to make progress on this. This just two quick examples. So Mike Blanton's work, for instance, could do this game, but now at high statistical accuracy, slicing up the mass function in this case, for instance, different concentrations of galaxies. Or of course, the environment, I will come back to this, played a big role then in analysis on SDSS data, and this is work from Baldry et al., where you then can look at the galaxy mass function in different environments, and this is one of the, I think, most robust evidences of something we now know and take for granted, which is the fact that more massive galaxies live in denser environments, and you have more low mass galaxies in less dense environments. But of course, it didn't stop there, and I think this is where the surprise started, where no one would have anticipated Sloan contributing that much to the field, is, for instance, stellar populations. You've got all those spectra. The spectra were reasonably good quality. You could work with those, but people could also stack those to very high signal to noise. So there was a very rich literature emerged over the last decade in stellar population properties. One of the things I'm personally interested in since the start of my career is basically trying to derive ages of galaxies, trying to understand how they have been forming, and in particular as a function of their mass. And these are early works where, with a handful of data, people looked at, and there are more of those in the literature, looked at stellar ages they derived for galaxies, correlated them with velocity dispersion of galaxy mass, and found these sorts of things. So these are scatter plots, but far from any sorts of correlation. And it was certainly not the fault of these teams here. They did a great work. This was really the status actually not that long ago, just 15 years. And I think Sloan has really made a huge step here. This is a simplistic picture, but from this very nice work of Kaufman and collaborators, not deriving stellar age directly, I will come to this in a second, but taking an age indicator, age metallicity indicator, really before there's an extra break, but something we really learned very well. We might have guessed it, but we could only see it that well with Sloan, is very clear bimodality in stellar population properties of with a transition mass really well defined with this kind of data. I think this is very amazing what could be learned here. And in fact, for the first time, you could really do proper statistical analysis, work that I have done now, deriving data, and this is now ages, deriving ages, similar plots like here, and now as age as a function of velocity dispersion or galaxy mass. And what you find is now a good correlation. You can see there's some bimodality, which messes things up a bit. If you have only a handful of galaxies, you're not going to resolve this. But if you have large data samples like in Sloan, you can see a good age-mass correlation. You can see element ratios and metallicity all show very clear correlations with galaxy mass, which led also, of course, to the now well-accepted downsizing picture of more massive galaxies forming first and being the oldest. Also, things like this is, again, some of my work contribution towards, I think this is coming up, sir, and the question of AGN feedback that Gabriela raised. There are many ways to look at this. This is one way, and again, a sample like Sloan makes this possible because with large samples, you can look at rare populations. What we've been looking here at is a color mass relationship, again, looking at different galaxies in different stages of classification, star forming, AGN, and passive here. And what we could see is that there is a clearly, in what is called the green valley sometimes, between red sequence and blue cloud, a transition phase driven by AGN, which now it's a long story that I don't have the time to really go much into, but we interpret as evidence that at least there's some part of it where AGN seem to be driving the truncation of star formation in galaxies and make them lead to passive evolution. And again, this only was possible because of large samples. Of course, beyond stellar populations, we learned a lot about gas physics in galaxies. This is the very, very famous BPT diagram that is used. Emission line ratios are being used to distinguish between AGN and star formation in galaxies. Very successfully. This is very important work. And of course, I think we all know Sloan has really changed this picture. If you go from this to here, you seem to have galaxies almost homogeneously distributed in this kind of diagram. And of course, with Sloan, at the latest in Sloan, we know that there's a very clear structure between star forming and AGN galaxies that is also now reasonably well understood. So clearly, the large samples here have changed a lot, and you can derive gas metallicities from this. And also, seminal work that came out of the Sloan data is gas metallicity correlates very well with gas mass in analog to the stellar populations, which is what you would like to see. But of course, this is very important, a very fundamental scaling relations for galaxies. And of course, last but not least, as my quick summary of what Sloan did to us is, for the first time, I think, with this large data set, we get a good handle on a galaxy environment. And we can now, this is a large area covered in Sloan, just plotting the galaxies, and you can turn this into proper environment measures. Many people have done this. There are many ways to do it that I can't really discuss here. I just want to say that this is done in low redshift in Sloan, and when we want to do this in environment, there are some service like EDIS that has done this, but we will have to resort to photometric surveys, and James will talk about the accuracy of doing this in his talk a little later today. And what we learned regarding environment, again, there's a huge amount of literature. I just pick a few here. Magically, some I've involved in myself. And this is the Peng et al. Paper, where you can see star formation rate is the color scheme as a function of mass and environment, and you can actually see that star formation rate does not scale at all with environment, but only depends on galaxy mass. And we've done something similar, but looking at the fraction of star-forming objects, and again we get a similar picture. It's galaxy mass driving these star formation properties. And likewise, the age-mass relation I've shown you before, when we do this in different environments with these various panels, they don't change at all. So what we've learned from this, and I think really Sloan has revolutionized this understanding, is that the environment, even though being incredibly important in setting up the structure of the universe, amazingly enough, and I still think this is one of the challenges in simulating galaxy formation and evolution, environment does not seem to be the primary driver of galaxy properties. It's the galaxy itself, it's the galaxy mass that tells us what properties the galaxy has. Then, of course, environment will come in as a secondary component. That's out of question in certain circumstances, but the primary driver is galaxy mass. And I think it's the large survey data that has really taken us to this interpretation. Okay, I want to switch gears slightly now, and what Sloan, of course, has done from photometry and the spectroscopy, single fibers on the center, giving us a global view of galaxies now. A modern surveys taking this further and try to dissect the inside of galaxies. Of course, IFU surveys have been around for a while. This is just a collection of some maps that then you can make per galaxy of kinematics and different stellar population indicators, emission line characteristics, and so forth. But now, of course, looking at gradients within galaxies, Sauron has been the survey with a handful of galaxies pioneering this, and now there are some more coming up. And we have already, actually before this, from long slit data, that was sort of the precursor of this kind of effort, learned interesting things like stellar population gradients in galaxies. Again, there's a lot to say. I just used this one example where we've learned, again, I think something amazing that we still have to understand how this came about in simulations, is that the gradient in spheroid, so in elliptical or early type galaxies, the gradient in age and the gradient in element ratio generally is constant. This is the Sauron version of it. You can see the age gradient in massive early type galaxies is flat. Likewise, this element ratio, while metallicity gradient, and there is some negative metallicity gradient. So there's clearly a lot to learn about how galaxies build up, outside in, inside out, what's the influence of gas accretion, and so forth, which we can learn once we dissect spatially and resolve galaxies. And that's the efforts that Sloan is doing now, at least in terms of galaxy evolution. So the Sloan 4 survey that has just started this summer, so Sloan 3 has transitioned into Sloan 4 in July this year, is again a cosmological component, which is EBOS survey, which I'm not going to talk about, but now there's a pure galaxy formation survey with it as well, which is called MANGA, Mapping Nearby Galaxies at APO, and the idea now is to use the fibers from SDSS, bundle them to fiber bundles, and do actually an IFU survey. And what is going to be new, of course, is that it's going to produce huge sample sizes, as we were used to do, and SDSS with individual spectra and simple photometry. Now we will have spatial resolved spectroscopy. Kevin Bundy is the PI of this, trying to find his way through the many fibers. So this is an example of the kind of hexagonal fiber bundle that we are producing. A major point here is that the spectroscopy remains the same, so good resolution and very large wavelength range. That's very important. But the key thing is now that we are going to get this IFU data for 10,000 galaxies over a 6-year survey. That's unprecedented, of course, and it's going to give us again, a sampling of galaxy environment for these kinds of studies that we haven't had before. So questions like what do gradients do, kinematics, stellar population gradients, and so forth, as a function of environment, could not be addressed or cannot really be addressed so far, I think, in an unbiased way, and this is going to give us the chance. I love this. just to show this is the sketch of the different fiber bundle sizes that we have in order to accommodate different sizes of galaxies. And this is what they are in real life. And I think it's really amazing triumph of technology, how regular the company is able to produce these fiber bundles. So this is going to be fantastic data, and this is Matt Bashady, he's Sloan 4 project scientist in the production of these kind of fiber bundles. These are the plates where they are plugged in. This is Niamh Ferrari, the instrument scientist, and really the instrument team has done a fantastic job over the last few years to take us to the current status, which is that we started indeed observing. And this is a propaganda picture from the Khalifa survey, which is nice, showing you've got color, magnitude diagram of galaxies, and now you can place basically the spatially resolved information along such a kind of diagram. This is just to give credit to other projects. There is Khalifa, which is taking this data of about 1,000 galaxies, and of course there's the Australian experiment SAMI, which is planning to get about 3,000 galaxies in this way, and then Manga with the 10,000 plan. So there's more out there, but these surveys, I don't have the time to compare them really, but they are certainly complementary in many ways, and we are working together to make this a good common effort. Now, another amazing thing about this Manga SDSS4 survey is that rather than just telling you what we want to do, and I could go on now for the rest of my time in order to tell you what the science driver is and what all our plans are, I can actually already show you some science papers, and I would rather focus on what we have now published within the collaboration, thanks to the effort of these 3 teams who have just put together 3 publications that have been submitted to journals based on prototype data that, however, give us quite a good idea about where the strength and the potential is going to be. So I go through those and briefly in the remaining 10 minutes or so. One is led by Cheng Li in Shanghai, and looking at the gradients and the subemission histories, diagnostics, I should say, in galaxies. And what I like about this is that it shows very much the potential of this kind of survey, which is the fact that we are using SDSS spectroscopy at its good spectral resolution and at the same time very large wavelength coverage. So for the first time, now this is not just a question of sample size that we are going to do with 10,000 galaxies, what others have done with 100. It's also taking current surveys much further by covering this large wavelength range. So you can start to make maps of galaxies for something like the D4000 angstrom break in the blue part of the spectrum, and a map of the H-alpha emission line in the relatively red part of the spectrum, taken and observed at the same time. So you get, of course, a fantastic diagnostics of stellar population, of gas properties, of kinematics, of galaxies in this way. In something, this preliminary study, certainly we are looking forward to more detailed studies on larger samples once they're coming in, has seen, for instance, that there are differences in gradients between these various indicators, and depending on, in this way, defined galaxies by centrally quenched or non-quenched galaxies. So you can see that galaxies that are centrally quenched show a gradient in the D4000 angstrom break, and while galaxies that are star forming throughout, well, in their center, they don't seem to show any gradient here. Further along these lines, you can also look at emission line properties. This is work being done by Francesco Belfiore and Roberto Maiolino in Cambridge, looking at the ionization patterns across galaxies. And again, the real excitement is you can do this with huge samples, but we've done this with just a few. But again, the wavelength coverage, I think, is something that has really what makes this work very new and shows the huge power of this, because now you can come with something I've introduced before with Sloan for galaxy populations, which is the BPT diagram, where you can do ionization classification within galaxies. And you couldn't do this before because the wavelength range wasn't large enough. You need to cover quite a large wavelength range in order to include H-beta emission line all the way to H-alpha and then 2 emission line, and maybe you want to take even bluer ones in there as well, or even redder. There are some very interesting red sulfur emission lines that help you, not just this one, and even red words of that help you distinguish the ionization state of galaxies. And so what can you do? You can, of course, learn a lot about things like gas accretion and AGN and feedback ionization, shock ionization in galaxies and so forth, how those might propagate and through galaxies, relate this to halo mass and environment and so forth. So that's an example of where you do this PPT classification. You can distinguish between star-forming galaxies and those with an AGN type or shock ionized galaxies, I should say. And in this particular case, but there are other examples that I just don't show here, you can very well see that your central parts of the galaxy, they are red, and they clearly show AGN ionization, and then you have this ring of blue, which is star forming, a ring of star formation around it, and you can even resolve it such that you see the transition, a mix of AGN and star formation in an inner ring exactly in between those two. So you have a very clear, obvious structure here where you seem to have an AGN in the middle and star formation around it. But you can also think of other concepts where you might have, where you would have star formation inside and all sorts of different ionization physics within the galaxy. And of course, you can also now look at gradients and metallicities and all sorts of elements in the gas and constrain gas accretion physics in galaxies. And finally, the last of this series of 3 papers that I want to show you in this talk is something we've done at Portsmouth. David Wilkinson, Claudia's student there, has written a code that Claudia will talk a little bit about as well in her talk, which is called Firefly, which is a spectral fitting code of stellar populations. And we've been using that in order to fit the spectra and produce maps of stellar population properties and physical properties in galaxies. Now, this is just a brief snapshot. I was just saying that. This is an example of a spectrum and how it is fit in this code. So what this code does is using stellar population models combined with different weights. What you then can derive is a full star formation history from your spectrum, and of course also quantities like light averaged ages and metallicities. But now, of course, with the IFU, you're going to do this in different positions in the galaxy. So now you have star formation history in each position within the galaxy that you want to study. And you can look at proper stellar population gradients. And this is the kind of result that you get. This is, again, just an example here and how you can distinguish spiral galaxy and elliptical galaxy from this sample here. And of course, the power is going to be that we do this for large samples and can distinguish all sorts of slice up our parameter space in galaxy properties, but basically as much as we like. So you can derive, these are maps showing, this is for instance the age of the stellar populations. You can clearly see older stellar populations, there's clearly the bulge and the star formation, the younger populations, very young populations actually in the disk around it. Likewise, metallicity, there's very little gradient here. Then for the early type galaxy, you can see that you've basically got old age across all the galaxy, and also only in this case, only very mild metallicity gradient. Then what this shows is the surface densities. Of course, you can nicely see again the bulge here and the disk around it, and your profile, and also mass to light ratios and many other properties, of course, that you can derive here and look at maps and turn this into one-dimensional gradients and study those properties as function of all sorts of parameters. And in particular, what I like is galaxy environment. I would say preliminary result, but already very encouraging from this study, is to look, in fact, at stellar population properties now in age, in stellar population age and metallicity, the mass average quantities now for different galaxy types. And you wouldn't really want to do this because it's quite a small sample. The point is that we will do this with many more galaxies, but just with the prototype data, we were already curious whether it's feasible and what we get. And in fact, already with a small sample, the result looks very, very encouraging. We find this is histogram now of age gradient, similar to the one I showed you early on in the introduction to this subject, and now distinguish between disk and spheroids. And you can clearly see a difference here. It's still statistically very noisy, so we need more data, but I think it goes in a plausible and right direction in the sense that you have no age gradient. That's what I was saying before. If you remember what has been seen in the literature before, no age gradient in spheroid galaxies, and you can now compare this with instead a clear negative age gradient in disk galaxies. And this contrasts with the metallicity gradient, where we do recover the well-known metallicity gradient in spheroids, and there might be some sort of less of a gradient in disk galaxies, even though, of course, the spread is very large here, and I think really we need more data to make a judgment call here. And we can now connect this very nicely to the gas physics that I've just shown you before. This is again coming to the PPT diagram, and what we can see here is, if you remember, this is the star forming region, this is the AGN or shock ionized region, and now we just paint those with the stellar population age that we have derived in stellar population metallicity. And I think it's quite fascinating what you get. Of course, you get younger ages down here, as you would expect, but it's very good to see that, I think. And you can see that your AGN and shock heated, and again, that takes us towards AGN feedback models. We are clearly dominated by old stellar populations. You can even see something which I find very fascinating. See the metallicity structure here. The BPT diagram, the ionization parameter, means this is low metallicity in the gas. And this tends to be high metallicity in the gas. And this seems to be reproduced in the stellar population. So we find lower metallicity stellar populations here, like in accordance with the gas, and higher metallicity here, which of course, again, is very precious in order to look at accretion, star formation models, how gas and stellar metallicities correspond to each other. Okay, this is all I wanted to say, just as a quick summary. Galaxy formation evolution. We heard also in Gabriella's talk before, there's lots of complex processes that we need to disentangle. Large data sets, I think the field of survey astronomy has clearly helped us to advance a lot here. This is not to say that individual galaxies are important, but certainly the surveys helped us a lot in understanding galaxy populations. Sloan 1 and 2 have done a large share here, and I think we are now continuing this legacy with Sloan 4 by looking at more detail inside the galaxies, and certainly exciting times are waiting for us there. And I'll stop here. Thank you.
Questions? Hi.
So the second to last science program you showed with the IFU observations, I'm not quite sure how to understand your statement that some significant fraction of the galaxy shows AGN like BPT properties. I suppose what you really mean is shock ionization in a significant fraction of the core, right?
Yeah, yes, I did say AGN and shock are almost together in most cases. You will have to distinguish those, of course, whether it's truly AGN or something else that produces shock ionization. When you find this kind of diagnostic at large radii in galaxy, you better not believe it's AGN, of course, because it's not in the center. Yeah.
Other questions? Last ask for other questions. You're obviously very clear, which is good.
Yep.
Okay, well, let's move on to Mike Gliders from Chicago. Give him a minute to set up. Thank you.
Okay, so I'd like to say a little bit about strong lensing in Sloan and in RCS2. I'll go a little bit beyond that as well. Some of what I'm going to say was well set up by a few of the speakers this morning. I'm not going to spend a lot of time motivating why strong lensing is interesting. I mostly want to talk about the process of finding strong lensing in large imaging surveys, sort of playing to the theme of the conference of the large digitized sky, and how do we exploit it in this specific science context. So I will start, if this works.
Last button.
All right, there we go. Before I do, people I collaborate with on the stuff I'm showing you here today, Everyone in italics is either a student or a postdoc, various institutions. Let me just start, because I'm a pictures guy ultimately, by motivating why strong lensing is interesting to look at by just showing you some recent Hubble images of strong lenses. These are various systems out of a big program that we've been running on Hubble, following up strong lenses found in Sloan. And they're interesting both in terms of studying background galaxies with very high magnification of various kinds, but also in studying the lenses themselves. These are mostly cluster scale lenses, because ultimately the strong lensing that we see in the universe should look like our theory and simulations predicts, and if it doesn't, we've got something wrong in our theoretical understanding of how galaxies work and how dark matter halos assemble. So it's been known for some time that strong lensing is a great place to understand halos. This, after all, is a quote from Zwicky's 1937 paper where he discusses basically the discovery of dark matter in coma, and oh, by the way, mentions that hence galaxies should be a great place to look for strong lensing, and hence a great place to look. You can see the age of the paper, right? Nebular masses. So, you know, we've known this is a good technique to use for a long time, but how to use it effectively on samples has not been all that well established. And, you know, the task really is, the simplest task I want to go through today is to find strong lensing in imaging data sets. And the challenge is you really want to find large samples with good completeness and high purity, and do so that in a manner that is well defined with those quantities understood, and ensure in that process that you've got a sample that you can actually talk to a theorist about, because that's what makes it the most powerful. So how have we done that? Well, basically, we've defined a set of lines of sight in these large imaging data sets like Sloan that we think are high payoff for finding strong lensing, which, given my background, basically means places that might have clusters and groups in them. We've then done a rather carefully calibrated visual examination that allows us to internally establish completeness. We do a bunch of follow-up to establish purity of the sample and how that kind of process results in a sample that's pure or not. And we're now working on applying this whole methodology to very sort of high fidelity image simulations to basically calibrate the whole thing and understand our selection functions from a theoretical perspective. So how did we get here? Well, you know, the basic history, right, is general relativity. And Zwicky published that paper in 1937, and then a whole bunch of people did a whole lot, nearly 50 years. Finally, you get the first strong lensing discovery in 79. The first discoveries in clusters. This is really most relevant for the stuff I'm talking about today. And since then, where have we come? Well, now we know of something like 600 strong lenses. A good resource for looking at all of them, if you want to, is this master lens database that Lexi Moustakis keeps going online. And you can sort them in various ways, by source, by lens, whatever you want. But there's a good number now compared to even just a few years ago. And this number is going up fast. So what have we done specifically in Sloan? Well, we've basically done a couple of things. So first of all, we've basically defined strong lensing as a morphological outcome, okay? That in Sloan, or in an image, strong lensing is something you can see based on the way that it moves light around in the image plane. That's a pretty reasonable starting point. It doesn't get you every single incidence of strong lensing, but you can calibrate when it doesn't. Basically because with sufficiently high quality data, as you saw at the start, strong lensing is really quite unambiguous, morphologically speaking. Nothing else looks like it. Now, we've done the search visually. We've actually looked at images. And the argument for doing this is, yes, you might want to eventually program a computer to do this, and people have worked hard to write such codes. But most such codes will ultimately be some sort of neural network that will be trying to imitate what we would do by eye and with our brains. To do that effectively, you need large training sets. And certainly when we started this work, there weren't large, well-defined training sets in individual data sets. So really, to do this process the first time, you actually really just have only one choice if you want to get a large sample, and that's to look at images. Now, we're actually really good at this, it turns out. And this is well recognized. You've probably all seen some of these online, right? You know, put in the letters you see so that we know you're not a robot. And you look at them and you go, this is easy. How come you can't program a computer to do this? Well, the reason is because it's actually a really hard task to program a computer to get all of these things all of the time. You know, these are actually called CAPTCHAs, completely automated public Turing tests to tell computers and humans apart. Why are we good at this? Probably for this reason. Where's the tiger? You all spotted it right away. A little harder, where's the leopard?
No, they did that.
Okay, where's the leopard?
Oh, yes, yes.
Okay, program a computer to do that. Now, and make it do it for both tigers and leopards in trees and in the grass and in the hallway of your building and everywhere else. It's actually really hard. We have tons and tons of evolution behind us and spotting things. Spotting complex signals in highly complex visual fields is something we're really, really good at. So what have we done? Well, so in Sloan, we have 4 examiners working independently. They basically get given color images that we've sort of carefully calibrated. Asked to give the image a score. 0, no lensing. 3, oh my God, look at that arc. 1 is not quite a 0. 2 is, it looks like an arc, but I'm not sure, basically. And they look at thousands and thousands of images. We pool the scores together. We can create a candidate list. Then we go to a small telescope to get better data than Sloan to follow up. That's easy with Sloan, right? Because that's about a high bar to get over. When you start talking about getting better data than a sample defined with Euclid, it becomes a different game, for example. We've done sort of 3 Sloan samples now, what I'm now calling the Sloan Giant Arcs Survey 1. It's about 50,000 lines of sight in the DR7 footprint. We added some other high latitude fields from DR8 to DR10, that's 1+. And then we've been doing another search in the entire DR10 footprint where we abandoned the idea that the starting point was a cluster catalog and just said, let's look everywhere where it looks like there might be a high redshift brightest cluster galaxy, so you don't even require a cluster anymore, because you're really looking for that backlight signature of the lensing itself. Now, because of the way we do the search, which includes giving examiners back images they've already seen without telling them tens of thousands of images later, we can calibrate the completeness of the survey internally, and we've done that. And so you can generate sort of completeness curves as a function of the mean score that was given to a type of object. We can also calibrate what kind of purity emerges from a search like this. I mean, the actual sample that results is pure by construction because we followed all the candidates up, but we can also calibrate the purity of this approach in a cumulative sense, starting with the highest score objects. Those are just pure. As you get down to about 2, the purity starts to drop off. Okay. Here's the final numbers for the Sloan 1 survey in detail. This is the total number of candidates, the fraction of those were followed up, the purity of those candidates based on the ones that were followed up, hence the confirmed number of strong lenses and the inferred total sample of strong lenses in that set after correcting for incompleteness in follow-up and incompleteness in the candidate list. Okay, so you're looking at numbers of a few hundred strong lenses defined rigorously out of Sloan using a single approach. The extension in area with the +1 to that was about another 35. And then we have another 60 odd out of the extension to higher redshifts by chasing BCGs. The 1+ extension, a lot of the SGAS1 sample was the HST images I showed you. But here's some stuff from the ground. This is our follow-up data. All sorts of interesting things, including, for example, this one's fun. We just got the Hubble imaging on this. This is a sextuply imaged quasar around a cluster, the only 3rd cluster lens quasar known, and the only one with 6 images, 1, 2, 3, 4, 5, 6. Also has an arc. This is at lower redshift than these and shows up in absorption in the spectra of the quasars. All sorts of fun things. Well, that wasn't supposed to be around that way. One slide didn't come through. That quasar is also highly variable, and we're measuring time delays for all the different images, including the central images, which leads to some interesting science as well. Here's the FGAS2 lenses so far, 60-odd systems. Now, RCS2, an imaging survey done at CFHT, a few magnitudes deeper than Sloan. You can see the numbers here. Let me just illustrate what this looks like. This is from back in the day when I was more interested in cluster cosmology than other things. There's a movie that's supposed to play and probably hasn't come through, I'm guessing. Let me just try. Let's see if... maybe I should use my own computer. Oh well. That was supposed to show the color magnitude diagrams of RCS clusters all the way out to redshift 1. It goes higher redshift than Sloan. Lets us define a bunch of other strong lenses, including this remarkable one here, which is one of the most massive clusters known in the universe. It shows up in the ACT sample, for example. Now, fine, you can find lots of strong lenses. What does it mean scientifically? How do you understand it? The big part of what we've been trying to do here is to define these in a rigorous, reproducible way that we could then carry over into simulations to really understand what the sample means. So I've been working with collaborators at Argonne National Labs on trying to do this using really big n-body simulations, including the largest simulation so far run, which is the Outer Rim simulation. The Star Trek fans in the audience will notice a naming convention here. The Outer Rim simulation is 1.1 trillion particles with more than 4 gigaparsecs on a side. This allows us to get robust strong lensing down to halo masses of about 10 to the 14. This is a somewhat smaller simulation, but in a significantly smaller volume, that lets us go down well into the group mass scales. And basically, we've built a new density estimator that allows us to ray trace these simulated halos really robustly. And we've built sort of a full image simulation pipeline on that ray tracing thing. So here's just a, there we go. This is just a sort of an advertising slide for the Outer Rim simulation. This is the full volume here, and you get down to individual clusters there. Okay, which one's simulated, which one's real? Votes for simulated here. Votes for simulated there. You're not even certain, are you? Can you tell now which of these 5 is real or simulated? Now? This is the real image. These are all simulated. Now, so why do we want to play a game like that? Because really there's one big question in this stuff, which is, does the strong lensing we see in the real universe, particularly for group and cluster mass halos, look like the strong lensing that we see in simulations? If it doesn't, something in our simulations needs work. The cores of halos are special places. It's where baryonic processes and AGN processes and feedback and everything else works really strongly. So it's a really interesting place to look to make a comparison. But the comparison when you do strong lensing isn't worrying about, oh, have I got my star formation prescription exactly right? Have I got a stellar population synthesis model that gives me exactly what I want? It's, do I understand the geometric process of, oh, I have a source that's producing some light, and GR tells me that light ends up here. It's a purely simple geometric calculation. The comparison itself is straightforward if you can get to the point where you can make the comparison, okay? And there's basically 3 things that drive your predictions around. The internal properties of the halos, this is where all that wonderful physics is. The cosmology, which affects the geometry, and of course pushes back pretty hard on this stuff as well, and the background sources themselves. So where are the challenges? Just a couple of slides left here. First of all, as we go forward into really large samples, we're at the hundreds now, as we go into thousands and tens of thousands, that terrifying slide that Yannick showed this morning, from SLACS, which is a big program that ran for years, to 2 months of Euclid data. We have to figure out how to automate understanding strong lensing in terms of modeling. This is actually, I didn't really mention this in my talk, but a great place to engage a broader community, because this visual examination doesn't rely on a PhD, it relies on eyes and a brain. So there's some interesting territory there. Simulations more and more are going to be key to understanding these samples. One of the challenges when we go to space-based images to do the definition of these samples is we suddenly lose a great source. So to build the simulations we build, we use the Hubble Deep Fields. Those are good enough to build ground-based images. But if you want to simulate HST quality images, you need 20 times better than HST quality imaging to put in the back end of the simulation to lens things forward, because your images are magnified by a factor of 10 to 30. There's only one way to forward with that, and that is to take data that we have and complexify it using various algorithms. This is just a really cool paper recently from collaborators of mine in Oslo. This is a simulated galaxy. This is a real galaxy. The simulation is done using algorithms taken out of video game coding. It's not physics per se, it's Perlin and structural noise and things. But it means you can produce millions of simulated sources that are sufficiently complex really easily. That's a simulated galaxy. You know, and you can run that on your laptop in a minute to get one of these, which you need to feed these simulations. Let me leave you with a final thought from an old movie that I like, because we do need to think about this as we get to thousands and thousands of square degrees of very high quality data. And I'll stop there.
Question?
Something which always leaves me a little perplexed about citizen science is that it is almost impossible to derive biases. So how can you, for instance, once you're done with this public project,
So,
how do you define completeness?
Well, completeness you can define basically, so completeness, you've got to be careful what you mean.
Yeah.
What I meant here was what I would call candidate completeness. I can tell you based on sort of the internal calibration of an image scoring process, what is the likelihood that an object that would have been given some particular score has been missed in that examination process? That is completely distinct from completeness in the scientific sense. You know, what is the likelihood that some particular manifestation of strong lensing has been found? You need both to actually get to a result. That second piece, you have to have simulations. You have to include, basically you want to take simulated images that are high fidelity, they look like the real data, whatever the real data is, and push them through the same selection process as you do for the actual data.
So you are going to have a technical example of a simulated image where you estimated the bias introduced by...
Absolutely. That's why we are working really hard to build literally millions of simulated strong lens images.
But you must be sure that the simulation and the simulation...
Absolutely. It's not trivial. Yeah, it's so what's probably going to happen is we're going to have to do this once, learn what we got wrong with the simulated images by comparing them to the things that were found, tweak, close that loop a couple of times. Yeah, it's not easy.
Okay. Other questions?
I was curious about your simulated galaxy image. It looks very amazing. Can you just make a comment on what goes in there? I mean, I suppose you have to predefine most of it.
So
What is the, when you run, I mean, how much is it dependent on what you put in, or when you run it? Is there some randomness that produces you different patterns?
yeah, okay, so here's how it works. We basically have in that image a cluster set of galaxies and a field set of galaxies. The cluster galaxies properties are drawn from large-scale cluster surveys like RCS2 or the follow-up imaging to the South Pole Telescope survey, or eventually internally out of surveys like Euclid and WFIRST, where these data will exist in very large numbers. The locations for those individual galaxies and their orientations, et cetera, and ellipticities and the like, are pulled by basically from the same simulated halo that is ray traced to do the strong lensing. We basically have a code that basically runs backward in time from the halo at the moment of observation to pick up all of the subhalos in the early part of the simulation and tracks them temporally forward into that present moment of observation, so you can find quite robustly where all the subhalos are. Those get painted with galaxies according to the real observations. The light cone is then populated by resampling things like the Hubble Ultra Deep Field, anything that's behind the cluster and close enough to the caustic that it might experience significant magnification, is fully ray traced through the simulation to produce the image in the image plane. And that's then all assembled. It's observed with realistic PSF, stars with realistic PSFs are added, et cetera, realistic noise, up to and including things like we take real observed flat fields, divide them into two sets, flat field one set with the other, use that residual for a large scale pattern noise term in the background of the image. A lot of little subtleties that your eye picks up really easily, but you have to really build in to make a convincing image.
Thanks, Mike. Okay, well, one quick question.
In your simulation of expected number of rotational lengths, what do you define? The number of the ground source, the number of lengths, foreground lengths, or just expected number of rotational lengths?
So, I'm not sure I understand your question. The numbers are fixed by the data. I mean, the inputs are basically a set of halos, which come out of the simulation, which have a set of internal properties, that comes out of the simulation, in a cosmology that sets the geometry, and have also set the properties of the simulation. And the background source population is set by observation. That's a purely, it's the Hubble Deep Field, basically, and candles and all that sort of rich ensemble of data. So there isn't really any free parameters at this point. Now, I haven't got to the point where I can tell you whether that comparison actually holds up or not, because of course the 20 years of literature says that it doesn't. We're working to get there. I'll let you know.
Okay, thank you. So let's come back here for the next set of talks at 22, please.
Hi. How you doing?
Can I try my computer?
Yeah, sure, please. Sì. Yeah, you better stay here because you will be streamed, right? I know that. Okay, so this is the camera. If you see from the maybe some of the so when you see check
Stanno pensando loro
so you talk about